Hi, everybody. This is Mr. Folly, who is again having pen problems, which is really kind of disappointing. This is Mr. Folly, and welcome to lecture number 2, where we are going to do parts 3 and so on. So we're going to look at the elemental composition of pure substances. Okay, pure substances are either elements or compounds. They're said to have one type of particle, and we'll see that better with pictures. Subscripts and compounds tell you a ratio of moles and can be calculated. This is called an empirical formula. To find the empirical formula of a compound, if you're given percentages, just immediately change the percentages to grams. No work, just change it, right? So if I'm 37%, I'm 37 grams. We're really doing out of 100. Convert grams of each element into moles, times dividing bar like we did last time. And then divide each answer above in step 2 by the smallest answer in step 2. This answer will likely be a whole number. It doesn't have to be, but it'll likely be a whole number. If not, it's going to be a simple fraction, like a fourth or 3/4 or a third or 2/3 or half. Those are the only decimals that you need to know. And if it is a fraction like that, then you multiply it by 2, 3, or 4 to get it to be a whole number. So let's take a look at it. I have 56.5 grams of carbon, 7.11 grams of hydrogen, and 36.4% phosphorus by mass. So we'll start with 56.5 grams of carbon, 7.11 grams of hydrogen, and 36.4 grams of phosphorus. Crazy things happening over here in Indiana. So I'm going to change this to moles. So 1 mole of carbon, I go to the periodic table, it's 12.01 grams of carbon. Okay. Remember, how do I get this? Carbon is right here, 12.01. And then I'm going to do the same thing for hydrogen. 1 mole of H is 1.01 grams of H. Same thing for phosphorus. 1 mole P is 30.97 grams of P. And let's get out our calculator and see what we get here. All right, so 56.5 divided by 12.01 is 4.704. 7.11 divided by 1.01 is 7.0396. And 36.4 divided by 30.97 is 1.175. So what I do next is divide each of them by the smallest number. So what this is doing is this is getting us everything into whole numbers. 1.75 divided by 1.175 divided by 1.175. So this one will be 1. Hey, that's a whole number. Let's see what 4.704 divided by 1.175 is. I get 4.003. That's 4. If I have 7.0396 divided by 1.175, and that's 5.99, that's 5. So that means my compound is going to be C4. Whoops, let's do it again. C4H5 H5P1. Okay? C is 4, H is 5, P is 1. Doesn't matter what order you put it in. Okay? All right. A store is selling hydrogen peroxide H2O2, and the liquid undergoes chemical analysis, finding it is 88.81% oxygen and 11.19% hydrogen by mass. Is the chemical hydrogen peroxide. So if it's got that ratio, it's going to be hydrogen peroxide, if that's what hydrogen peroxide says. So let's see. 0.881, 0.881 oxygen, that's grams right away, right? And 0.1119 grams of hydrogen. 16 grams of oxygen, 1 mole oxygen, 1.01 grams of hydrogen, 1 mole hydrogen. So let's see what we get. 0.8881 divided by 16 is 0.0555. 0.1119 divided by 1.01 is 0.1108. So what I'm going to do is divide these both by the smallest. 0.05 is smaller. And that's going to be 1 dividing by itself, right? 0.1108 divided by 0.0555 is 2. So what this is this is going to be OH2 or H2O, right? So no, it is not hydrogen. All right, to find the molecular formula. So the empirical formula is the reduced formula, right? To find the molecular formula, you find the empirical formula and that empirical formula's mass. Go to the periodic table and add it up. Divide the molecular formula mass by the empirical formula mass. This will give you a multiplier for the subscripts. So let's take a look. Commonly used desiccant. A desiccant is something that sucks the water out of things, dries it out, is 43.642% P and 56.358% O. If its molar mass is this, what is its molecular formula? So again, 0.4368 grams, 43642. Man, I'm making up some numbers. 43642 grams of P, 0.56358 grams of O, and then it's 30.97 grams of P from the periodic table. And then it's 16 grams of oxygen and 1 mole of oxygen. And I'll do the math for that. So I have 0.43642 divided by 30.97, and that is 0.01409. And then I'm going to do 0.56358 divided by 16, and that's going to be 0.0352. Now divide by the smallest to get into whole numbers. Divided by 0.019, divided by 0.004. I swear, I can do better. 0409. 0.01409. This is going to be 1 divided by itself. And that's 1.0352 divided by 0.01409 is 2.5. Uh-oh, this is the first time I don't have anything close to a whole number. So this is 2.5. So I have to multiply this by something to make it a whole number. That something is 2. So I'm going to multiply both of these by 2. So that means I'm going to have P2. See how P got to 2. And O is going to be 5. Okay? So that's P2O5. So now what I'm going to do is I'm going to do a ratio of the masses. So I'm going to go to the periodic table and add these up. So phosphorus is 30.97 times 2 plus quantity 5 times 16 is 141. So this is 141.94. So this is my EMP mass, right? So this is my molecular mass. It'll always be bigger. So 283.89 over 141.94. Even my eyeballs can tell you that's 2. So what I'm going to do now is I'm going to double. I'm going to multiply these subscripts by 2. P4O. 10 is my molecular formula. Okay. A compound will have one empirical and one molecular formula. Every once in a while, they're the same. Sugar's molecular formula is C6H12O6 for any sugar, assuming it's sucrose, in the world. The empirical formula is that formula reduced. See how I can divide each of these by 6, and I get CH2O. That's the empirical formula. A molecular formula could be common for two different compounds. So all of these formulas, if I write them out, are the same, right? So there's C4, H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, H10O. But these are different things because they're arranged differently. Okay? So each of these are C4H10O. Empirical formulas could be common as well, but look for reducible things. So C6H6 and C10H10 would be CH. All right, so now, compositions of mixtures. Mixtures have a blend of properties. Compounds have brand new properties, okay? Carbon is coal. Sugar, not coal. Sugar is sweet. Yummy. Hydrogen explodes. Sugar doesn't explode. Oxygen, breathe it. I'm alive. Sugar, breathe it. Oh, that hurts just thinking about it. It's like worse than the cinnamon challenge. Okay, so compounds have new properties. You should know that. Salt waters, get the idea. Water is a pure substance with unique properties of its components. Same deal. Hydrogen explodes, breathe it in, and it changes your voice. Oxygen burns, keeps you alive. Gas. Water puts out flames, kills you if you breathe it in, and it's a liquid. All right, list of mixture tricks. If it says the word solution, it's always a mixture. Impure things are mixtures. Graded things are mixtures, not like assignments, but there's an 87 grade of gasoline or an 89 grade of octane. Formation of compounds versus formations of mixtures. So there's signs of a chemical change. New substance is formed. That means it's making a compound. You'll see a color change as long as you're not painting it. A gas will be released as long as you're not boiling it. A precipitate forms, so chunks form out of nothing. A new substance formed, not a new state of matter. Remember, steam is still H2O, just like liquid water is H2O. Heat is absorbed or released as long as it's not a phase change. And energy, often light or sound, is absorbed or released, not a phase change. So now AP Chemistry loves particle diagrams. And this is where I get to introduce little baby Chucky. So little baby Chucky has pictures. These pictures, I say little baby Chucky's an excited 5-year-old. Use basic shapes like squares or circles or triangles. See, I use circles here. If two things are touching, that means they're bonded. Or I hold your hand, we're bonded together. Like I love my mom and I hold her hand wherever she goes. If the same thing is touching, it's a diatomic element. And that's bonded, right? Touching means bonded. Touching, not touching. Little baby Chucky, no touching and not touching. If it's at the bottom of the container and neat, it's a solid. See how this is neat? It's bottom of the container and twisted and jumbled, that's a little jumblier. If it fills the container and the gas, it's not very full, that's a gas. And whooshies indicate temperature. All right. This is a diatomic element. Okay. This is a diatomic element. See how it's the same element, red circles touching. Same element, white circle touching. This is a mixture. This is a compound. So do you see how if I put hydrogen and oxygen together, I'll probably just get a mixture. I have to do something special to make it turn into water. Adding energy, do some kind of energy thing to it. Okay? Homogeneous and heterogeneous mixtures. The word homo means the same. Well, what's the same? Every sample is the same. Okay? Heterogeneous mixtures, not every sample is the same. Check lots of locations. All right? So now we have a chemical determination of purity. So there's a lot of questions that say, how pure is this? Is there something else in it? What percentage of it is there? Okay? Sample 1.4, number 1. To be honest with you, we had 15 minutes. We'll do these samples in class, but I'll make another video for the samples too. So we'll take a stop right here. So I will talk to you later. Toodles.